Thanks for the kind introduction. So I want to talk about a number of surface analytical techniques which we use for various applications. 2/3 of our research is for our own group and a third is in collaboration with other groups. And what I have done today is I've selected a few examples which illustrate how these techniques can be used, for example, in collaborations. The questions we usually ask is, what forms the surface? What forms the outer layer of a surface? What is the electronic structure of the surface? And what is just below the surface? And here are 3 examples. Here's a photovoltaic device. You have interfaces. You want to know what is happening at the surface and at that interface. Here's a coating of a surface. You want to know how you actually have coated your surface. How's the covering layer structured? And here's an example which is quite different to the others. It's a liquid surface, and here we ask the question, what is actually forming the outer layer of that liquid surface? What surfactant goes to the surface? What salts go to the surface? So let's start here with a photo of the equipment. So there is a range of techniques included, and the ones I want to talk about here today is called Metastable Induced Electron Spectroscopy and this NICISS, this concentration depth profiling technique. They are all integrated in this equipment here. And we have 2 similar equipments doing similar things on these for these investigations. So let's start with the ion scattering technique, which is a depth profiling technique. Let's say it's a surface here composed of 2 species, a red and a blue species. You fire an ion onto the surface. Ions getting backscattered, loses energy due to the backscattering process. And from that energy loss, you can determine what was the mass of that atom which you have hit. If the projectile penetrates deeper into the layer, into the sample, then you lose additionally some energy, and it's from the surface up onto the depths from which you're backscattered and back to the surface. So that provides depth information. And what we then get is a concentration depth profile like what's sketched here. So for red species enriched at the surface, and the blue species depleted at the surface, and that is here plotted on an angstrom scale. So this is the resolution we can achieve with this method. Here's one example. So let's go back to these polymer-based photovoltaic devices. So here's a top polymer layer, and on top of that is an molybdenum oxide layer deposited. And here's now the concentration depth profile of that molybdenum oxide. You can see here is an increasing thickness of that molybdenum oxide. You can see that with the deposition, you grow the thickness of the layer, but you also grow how much is in that layer. So only here we have formed a closed layer, and that closed layer then has a thickness of about 7 nanometer. The other class of techniques we apply is electron spectroscopy. The most well-known one is X-ray photoelectron spectroscopy. I won't talk much about that. All electron spectroscopy techniques have the same, let's say, way of working. You deposit some energy, electrons in your sample pick it up, they are ejected. And what you basically do is you probe your electronic structure, which is here. So here's the bound electrons. They get additional energy, and you basically reflect what is here a bound electron that's then reflected here as an emitted electron. When you then measure the energy of these electrons, you basically learn what is the composition of your sample. So here's a quite different techniques. Again, electron spectroscopy, but rather than taking a photon, you take a metastable helium atom. The reason for that is now illustrated here. Let's say for a disordered surface, you would see all contributions from the various parts, let's say, of this molecule forming the outer layer. And you would get the spectrum like that. So you would have from all 3 components, you would see a feature in your spectrum like what's illustrated here. However, if you have an ordered surface like this one here, these metastable helium atoms, they would see only the very outermost layer. And that's then illustrated here. You would see exactly only this component and nothing else. No other electron spectroscopy technique can facilitate that. Here's an example what the technique also can do. So we can also measure the valence electron structure. And I don't want to go into all the details. It's the same type of polymer, molybdenum oxide, what's deposited here. This one here is now facilitating measuring the electronic structure. And here we could determine that there is a very strong potential gradient formed at the surface. So that's what these techniques can facilitate. However, what is also quite interesting is that you can determine how do these layers actually look like. So what structure would you get? Let's say if you would be aiming to cover a surface, let's say a gold surface with such a structure here, would you eventually get this structure at the surface, or would that look differently? And this is a question which the technique which I've just introduced can actually answer. First, let's go back to the depth profiling technique. So we have two spectra here, and the ion scattering spectra. So the black one's just from the substrate only. The green one is from the substrate plus that overlayer. And from that shift in the spectrum, and I don't want to spend the time to explain how the shift comes together. That's basically the energy loss of the projectiles in that layer. From that shift in that spectrum here, we can determine how thick that overlayer is. And we've found here the thickness of that overlayer is 3.9 nanometer. So that's now measuring how thick the layer is. But the other question is now, how well ordered is that layer actually? And that's what we could determine here. So here you're back to the, we're back to that coating layer on that gold surface. And we had applied two different conditions. And one, we got a very close packed structure. And here we got a very loosely packed structure. And the difference between these two, we could determine with the electron spectroscopy technique with the metastable helium atoms. So we could show that this surface is in fact terminated by CH3 groups. So we saw only these ones in the spectra. And here you found that the molecule is actually lying flat on the surface. So we can determine the structure of the surface, the thickness of the surface on that level of accuracy. Now jumping to a complete different subject, as I introduced earlier, so we can also look into liquid surfaces. And here's an example of a solution. So that's the solvent's called formamide. Doesn't matter too much if you're not a chemist what that actually means. It's a polar solvent similar to water. And here's a surfactant. Again, the exact structure doesn't matter too much. But what you can ask is how much of that surfactant is actually at the surface. And we can do that with this depth profiling technique. So here's plotted the depth scale. That's in angstrom. Here the concentration, and that's the exact concentration of the solution. So it's an explicit concentration in mole per cubic centimeter. You can see here at the surface, so in the range of the surface, so 0 is the surface, you can see an enrichment of the surfactant at the surface. And from the shaded area here, we can actually determine exactly how much of that substance is on the surface. So these are three examples how we use these techniques. There's a range of other applications. And as I said, so 30% of our time we spend in collaboration with external users of these equipments. And if you have further interest in looking into these things, so here's a link to the website of the Flinders Institute for Nanoscale Science and Technology. And here's the Flinders microscopy and microanalysis. And with that, I want to thank you for your attention.
Good afternoon, Gunther. Thank you very much for sharing that with us. You're also off the hook. I think everyone's getting a little tired perhaps and we're not getting questions. So sorry, I can
just send one question.
I've just got one. Oh, okay. Sorry, literally, we just have a question. From G, can MIES measure the grafting density of polymer chains on the metal surface? And how accurate would it be compared to ellipsometry? Is that right? Yeah. Right, thanks.
So ellipsometry could give you only the average of the surface. It wouldn't give you any information about orientation and how it's distributed. So MIES is capable to tell you exactly how that layer is forming and how thick that layer actually is.